Okay, thanks very much. So the next talk will be given by Jiawei Chen, titled Synchronous Programming with Refinement Types.
Hello, everyone. I'm Jiawei Chen, and today I'm going to be talking to you about our work in bringing type theory and robotics together with synchronous programming. Now, we like to work with cyber-physical systems, or CPS, and these consist of a piece of software that interacts with the physical environment. So think of things like industrial controllers, like a water tank controller, or unmanned aerial systems. Now, one of the issues with some of these systems is that they have really stringent safety requirements, which means that they require formal verification to get strong safety guarantees. But the issue is that a lot of these CPS tools that are designed for verification don't make it easy to implement actual CPS in the real world. On the other hand, tools that are designed for implementing CPS don't really lend themselves well to being verified. And so there's kind of a gap here, and we don't think that CPS designers should need to choose between a tool that allows for verification or a tool that allows for implementation. So why can't we have both of them? Why can't we be in the center of this Venn diagram here? And so the first part of my title is synchronous programming, and we're pretty big fans of synchronous programming because it's had a proven track record in industry. So for example, languages like Lustre, Scade, Esterel, Signal. Scade in particular, which is inspired by Lustre, has been used by Airbus to develop actual avionics systems and software. So there's quite a bit of a track record here. Now, synchronous programs interpret data that comes into them as streams over time. So you always get data that comes in, and they operate on this data and then produce an output stream. So think of everything as just a bunch of streams and stream manipulations, and that's how synchronous programs operate. Our work in particular is based on Zulus, which is a functional extension of the Lustre programming language, which includes hybrid systems and the ability to model and simulate these. Now, we've heard hybrid before, and it's sort of an overloaded term here, but hybrid in our case refers to a system that includes both discrete and continuous time components. So these are quite useful for modeling real-time CPS because of the use of continuous dynamics. Now, streams in Zulus are built using something known as a unit delay. You'll see this a lot. It's called like the follow by and recursion. So follow by, or a unit delay, works like this. So if you have a stream S, another stream T, and you want to define S followed by T, this stream first looks like the first value of S, and then for every time after that, takes on the value of T, but delayed by 1, hence the unit delay. And it turns out that a lot of interesting programs in Zulus can be constructed by using unit delay and recursion. Now, I mentioned before that Zulus handles hybrid systems, and to be clear, our extension to Zulus doesn't really handle the hybrid part just quite yet. This is work that we're currently undergoing right now. We only look at the discrete part, but we hope to eventually extend this to support full Zulus. Now, the second part of my title here is refinement types. And well, we're pretty big fans of Liquid Haskell, and apparently a lot of you are as well. So what's really nice about this is that we get some decidable SMT-based type checking and subtyping here. And so it turns out that a lot of the things that you see from Liquid Haskell we can carry over, but with some adaptations. You've seen this all before already in previous talks, so I don't think I need to really go into depth about this, but refinement types basically have some sort of logical quantifier or some predicates. But when you extend refinement types to streams, we note that these predicates now become temporal properties. So you're not just talking about one period in time, you're actually talking about the entire history or the future behavior of an entire stream. So hence, you now have temporal properties. Now, our specification grammar, shown here in the lower right of the screen, covers a subset of LTL. Namely, we only look at things like the always, or the global operator, and the next operator. So these tell us that something either always has to happen or happens in the immediately next time instance, respectively. We hope to support a full set of LTL in future work, but we note that for now, always and next are generally speaking enough for most safety properties, which is what we're primarily interested in. So in short, we formalize refinement types for synchronous language, prove type safety on this language, and implement verified programs on physical robots, and we have some empirical results too. So everyone, meet Marvelous here, the method for automated refinement type verification of Lustre. Now, the way Marvelous works is you take specifications and code, and you put them in a type checker, and you either get a counterexample to refine later, or you produce a program that can be compiled to either simulate or execute on a real system. And we have separate compilation paths to support these two. This is facilitated using the models keyword. You can find out more details about it in the paper, but it makes it easy to separate these into separate paths to either simulate or execute in real time. Now, as mentioned before, we verified discrete time subset of Zulus, noting that Zulus gives us the option to eventually extend our work to support hybrid systems in the future. So, in short, here our contributions are to formalize a refinement type system and semantics for this language. We've implemented a type checker inside Zulus, which you can also see in our artifact. And finally, we demonstrated real-time execution of verified Marvelous programs on real robots in our lab. So this is a simple Marvelous program here. It's basically, we're defining the variable x as a stream that starts out looking like the number 1. And then for every time step after that, we define x as having the value of x plus 1 from the previous time step. Note the use of the unit delay or the follow by operator here. So let's try to keep track of what values x will look like. So to begin with, x takes on the value 1. And so therefore, in the same time step, x plus 1 must be 2. In the next time step, x then takes on the value of x plus 1 from the previous time step, so now it becomes 2. And so x plus 1 must equal 3, so on and so forth. We're essentially counting the natural numbers here. Let's say our system designer then wants to specify that x should always be positive. So she adds a refinement here. And note that always be positive is encoded using the LTL operator, so the box operator here. And it's encoded in our refinement type here. So how do we verify this program then? Well, let me pull out my box of things that we're going to send to the SMT solver here. And so we first look at the top level here, that we have a follow-by expression. So if we want to show that a follow-by expression is always positive, it needs two things here. We first need to take a look at the left-hand side, or what we initialize the follow-by expression with, which is 1. So we first need to show that 1 is positive, and that's pretty straightforward. And then because we've recursively defined the variable x, we can first assume that x is positive, and using this assumption, we need to show that x plus 1 is also positive. Now, a lot of you are probably saying that this looks a lot like induction, and you'd be absolutely right, and this is exactly what we're doing here. We're proving that x is positive through induction. And so all these verification conditions are generated syntactically based on the set of typing rules that we've created for this language. More details can be found in our full paper. And so once we verified this, what we can then do is we can pass along this verification result to other parts of the program, knowing that all x's are now positive. And so this makes it a nice modular verification. Now, how do we know that verification is correct? Well, we do it the typical way. We need to prove type safety by first determining the semantics and the typing rules of the language. Now, the semantics here are very similar to the standard semantics of Lustre. They're all stream-based semantics here, but we had to adapt them a little bit to make our type safety proof syntactic. Now, they look a little similar to the small step semantics you might have seen before, but these are actually completely different here. So when you have a term e, it emits a value and then rewrites itself for the next time step. So our semantic judgment shows that in some environment, which we've divided into a separate component for functions and another component for term variables, an expression e first emits a value and then rewrites itself to a new term. Now, the key difference here is that only one step gets taken per time interval. So at each time step, you only take one semantic step. On the lower right here, I've shown you my favorite rule here, which is the rule for a unit delay or follow by. So if you have an expression E1 followed by E2, we first evaluate E1 to obtain the value V1, and then the follow by expression emits a V1 and then rewrites itself to the delayed version of E2. Now, this delay operator is wrapped around E2 to help the evaluation of E2 in the next time step stay in sync with the environment. We have some more details about that in our paper. The other half of this is, of course, we need typing rules. As I said before, we're pretty big fans of refinement types, but we can't really just use refinement types out of the box here. We have to take into account that we're working with streams here. So like the standard refinement type system, we have our usual environment here, but again, also broken up into functions and terms separately. You have some term that types to some value tau. It's pretty standard stuff here, but we need to deal with streams and temporal predicates as well. And critically, the fact that because our stream programs are rewriting themselves constantly, the type that we can assign to our stream today might not work for the stream we have tomorrow because our stream is evolving over time. So we need to define a way of saying how to relate these streams that we have today to the streams we have in the future. And the semantics of these are detailed in our paper as well. And so again, we have my favorite typing rule here, the corresponding typing rule to the semantic rule for unit delay, where we have some E1 followed by E2. And the typing rule here says that E1 followed by E2 first looks like E1, and then for all time after that, note the temporal operator here, it will behave like E2. And so, of course, along with the syntax, the semantics, and the typing rules, we also need some form of syntax-guided type safety. And of course, we also need to make modifications likewise here. So we also have to account for the fact that because our types don't exactly stay the same throughout time, we need to sort of modify the usual progress and preservation lemmas to account for that. And so we made some tweaks to the meta theory to account for our stream types. Speaking of, our main theorem for type safety states that under some assumptions of the environment, well-typed terms always step to terms which are well-typed in the next time step. And that's the key part here, is that we can't just type things in the same typing context. We actually need to change things. And the semantics of how we change these types are detailed in our paper. And so, of course, this makes all the type theorists here happy. But, of course, we also need to work with some roboticists here. We need to work with actual robots in the lab. So we've implemented and then verified an adaptive cruise controller, an autonomous braking controller on actual robots in our lab. And so a nice property that you can have is that if you're trying to follow another robot, you don't really want to crash into that robot. That would be pretty bad. So we want to ensure that the distance between our robot and the robot in front of us is always positive. And so that's a nice safety property to verify. For now, we're just worried about the control logic at the high level. So we're going to assume that all the hardware abstractions and the sensor drivers and everything below that level are trusted, although that could be future work. In our experiment, we verified this autonomous braking controller, and then we've implemented this on an actual robot, such as this one right here. We note that in our experiments, we can actually follow moving vehicles in real time, and we've never had a single crash in any of our experiments. And here we've got a little video of one of these experiments running. You can see our robot behind us is running the verified code, and it's following this robot in front. As you can see, please stop. Hooray, no crash. So as you can see here, a verified Marvelous program can run in real time, and as you can see, our two robots are still in one piece. So this is what the compilation and workflow looks like currently in Marvelous. We start out with the specification on some program. We then verify and compile this program and specification to obtain a verification result. And then finally, we apply that verification result to obtain an end-to-end guarantee on safety when we execute our program. Now, of course, Marvelous is still in development, and we see many areas that we can improve. Specifically, on the specification side of things, we'd really like to support hybrid programs, because we're currently only dealing with discrete programs, but we note that a lot of CPS are hybrid in nature, so we have some continuous components as well. And of course, being based on Zulus helps us with that to reach that potential. We'd also like to implement a fuller set of LTL specifications. Namely, we don't really handle the finally or the until operator, but these could be useful for some applications. On the verification side of things, it'd be nice to be able to generate invariants rather than require the user supply them. Now, works such as Kind2 already deal with invariant generation using some form of K-induction, and it'd be nice to include some of this into our work as well. On the other side of things, it'd be really nice to guarantee that whatever verification results you have on theory can actually be applied to the final executable. And so there's been work like the Velus project, which has shown a formally verified compiler for synchronous programs, and it'd be nice to incorporate that work into our workflow as well. Finally, on the execution side of things, it'd be really nice to support some more hardware platforms. So we only support these like little wheeled robots, although they're really adorable and kind of cute. We would like to eventually support other robotics platforms, such as autonomous aerial vehicles. Also, we'd like to support some form of runtime monitoring. Because we do everything compile time, we need to be sure that at execution time, that all of the assumptions that we make during verification can be carried forward and are actually maintained when we execute. So, to summarize here, robots and other cyber-physical systems require formal verification to ensure that they're safe. We provide that using a unified robotics platform by taking synchronous programs and enhancing them with refinement types. And then we've demonstrated that marvelous programs can execute in real time on real hardware. And before I conclude, I'd like to thank these wonderful people that make this project possible, and I'd like to open the floor for questions. Thank you.
Thanks for the talk. In the grammar of your specification language, you support nested modalities, and you only show the rule for globally, but not nested modalities. So do you actually support nested globally, for example?
Let's see. So in the specification grammars here, this one, right?
Yes.
Yes. So you mentioned I think you said less than, right? Or
for example, if you have globally A and next globally B or something like that. So how do you deal with that case?
Can you repeat the question? Sorry.
Or maybe you can show there was an example with a rule for globally, the one with the invariant.
Was it this one?
Yes. So what if instead of just globally x greater than 0, you have actually another globally inside of the first globally? Like globally x greater than 0 and globally something.
Right. So in our instance, we deal with only like deterministic programs. So I guess in that case, there really isn't a sort of notion that something, that some form of like, all like universality for all traces here. But yeah, I'll have to think about that. But
okay, we can take.
Let's see.
Go ahead, Neil.
Hi, this is really nice work. Like synchronous languages and refinement types are two of my favorite things, so that's good. One question I had is, in your specification language, can you express properties like, this in this example here, you might want a property that says x is increasing at every time step. Is this expressible in your specification language?
Yes, we actually can. So, for example, if we use the unit delay, we can specify that we have some variable, like let's say y, that is just x from the previous time step. And so now we can say that, let's say that y must be less than x, and therefore we can then get some notion that x is always increasing. So it's not something that's like supported first class in our language, but it is totally doable once you add some additional variables.
Okay, thanks.
Let's thank our speaker again.